Hello, everyone. Thank you to the session organizers for inviting me to present in this session. Today, I will be talking about developing and testing a ground motion-based earthquake early warning algorithm for the U.S. Shake Alert system. The earthquake early warning system we have in the United States is called the Shake Alert system. Shake Alert is operated by the U.S. Geological Survey in close collaboration with state and university partners. Shake Alert has been operational for several years now, with public alerts available in the state of California since 2019 and in Oregon and Washington since 2021. Shake Alert takes a source characterization-based approach to earthquake early warning, where once it detects an earthquake, it first calculates an earthquake's magnitude and location information, and then inputs these parameters into ground motion models to compute the alert regions. Shake Alert estimates source parameters using different early warning algorithms called EPIC, Finder, and GFAST. These algorithms leverage different data types and different types of observations to estimate the source parameters, so they each have different strengths that help Shake Alert better span the range of earthquakes that are expected for the U.S. West Coast. However, there are still situations that can be challenging for source characterization approaches, such as large earthquakes where it takes several seconds to reach a high magnitude estimate, as well as active aftershock sequences where there are many earthquakes in a short period of time. And this is where incorporating a ground motion-based earthquake early warning approach could help. The ground motion-based approach we have been investigating for the United States is called PLUM, or Propagation of Local Undamped Motion. PLUM was originally developed in Japan and is in operation in the JMA early warning system, but we've made some adjustments to how PLUM works in the United States to get it to better correspond with elements of the Shake Alert system. These images show simple schematics of how PLUM works, where the rows show different snapshots in time. First, we have the observed intensities at the station. PLUM then forward predicts the observed modified Mercalli intensity at these stations to a set of prediction points within a given radius of these stations. Then, these intensities are projected onto a predefined alert grid. We are using the same alert grid as the Shake Alert grid product, which is a 0.2-degree grid or about 20-kilometer grid spacing. Because of this small alert grid size, we have had to increase the forward prediction radius to 60 kilometers in order to achieve suitable performance. PLUM has had very promising results in our internal real-time testing. However, we have found that PLUM has been challenging to integrate into Shake Alert operations, primarily because Shake Alert aims to produce ground motion estimates that correspond with median shaking observations, which is difficult to achieve with the PLUM approach. So we've modified PLUM into a new configuration called APPLES, or Attenuated Propagation of Local Earthquake Shaking. APPLES adds an attenuation model in the forward prediction step. So instead of the same MMI value assigned within a given radius of a station, APPLES produces shaking distributions that decrease with distance from a station. We found that APPLES can reduce over-alerting during smaller earthquakes because of this varied intensity with distance, and that for large earthquakes, APPLES is able to provide longer warning times compared to PLUM because it's not restricted to the set alert radius. And that leads us to the main purpose of this talk, which is to present refinements to the APPLES approach. Our main motivations for these additional adjustments are to reduce over-alerting during smaller earthquakes caused by localized high-amplitude observations, and to make the APPLES intensity estimates even more consistent with the Shake Alert goal of corresponding with median shaking observations. And finally, we want to perform a direct assessment of APPLES with Shake Alert. We investigate two main configuration changes in this work, and these changes are shown in the example schematic. The first option is in the step where we assign intensities to the prediction points. We look at rank 1, which corresponds to the maximum observations from the stations, or rank 2, which uses the second highest station observation. The next option we test is where we assign intensities to the alert grid cells. We choose between assigning the maximum or the median intensity from the prediction point values within each grid cell. And we're going to call these different configuration options by their different combinations. For example, rank 1 maximum. Our original apples configuration took the rank 1 maximum approach, and to jump ahead to the results, we found that after this testing, our new preferred configuration is the rank 2 maximum approach. So please keep that in mind when I show you the results of our testing in the rest of the talk. We ran simulated real-time tests of the 4 apples configuration options, as well as Shake Alert, using the Shake Alert test suites of the US West Coast and Japan earthquakes, totaling 110 events. We then did several performance analyses, focusing on direct comparisons to the station observations, and then alert quality and warning time comparisons using consistent alerting strategies across all approaches. Before we go into the overall results, I want to start off with a couple of specific example earthquakes. Here is an example of the magnitude 4.7 Tres Pinos earthquake, which occurred a little south of the San Francisco Bay Area. It had very high ground motions close to the epicenter, likely caused by topographic amplification, including an observation of MMI 8.2. The top row shows the maximum estimated intensity distributions from the different early warning approaches, and the bottom row shows the comparisons between the maximum estimated intensities and the corresponding intensities from the shake map. Our original apples rank 1 maximum approach has ground motion predictions that are dominated by this single station, which leads to significant overestimation compared to the shake map observations. Apples rank 2 successfully ignores this station in its forward prediction procedures, which allows it to produce shaking estimates that match well with shake map. Shake Alert has a very high magnitude estimate for this earthquake due to the near source station observations, with a peak magnitude estimate of magnitude 5.5. However, the ground motion estimates correspond very well with shake map, though there is some overestimation at lower intensities. Here is another example. This is the magnitude 6.4 Ferndale earthquake, which occurred off the coast of Northern California near Cape Mendocino. This earthquake occurred in a region of dense station coverage. So while there is a slight reduction in intensity estimates using Apple's rank 2 maximum compared to Apple's rank 1, there's not a huge difference. Shake Alert also had a good magnitude estimate for this earthquake, only slightly higher than catalog values, with a peak estimate at magnitude 6.6. However, we see that Shake Alert tends to underestimate shaking at higher intensities and overestimate shaking at lower intensities for this event. These plots here show warning time comparisons for the 3 early warning configurations, where we have the fraction of a given intensity category with a given available warning time relative to the S-wave arrival. Here, I'm showing warning times using an alert threshold of MMI 3.5, which is the intensity threshold used for alerts delivered via the wireless emergency alert system in the United States. We can see that all 3 approaches produce similar warning times, especially at the higher intensity levels shown in the warmer colors in the solid lines. Now, if we increase our alert threshold to MMI 4.5, which is shown in the bottom row, we see that the available warning times with Shake Alert are significantly reduced. However, warning times with apples are unaffected. And this suggests that apples may improve Shake Alert's performance for users who require higher alert thresholds. But let's confirm this by looking at more earthquakes. Here are the results summarizing the comparisons to the observed ground motions. These plots show empirical cumulative distribution functions of the residual between the predicted shaking intensity and the observed shaking intensity at the station for each early warning type tested. We computed the residuals for each earthquake individually, and then we found the percentile distribution across all events. Because the Shake Alert system aims to match median observations, we prefer early warning performance where the median behavior intersects at the 0 residual. So looking at these distributions, we can see that Apple's rank 1 maximum shown in the green always produces shaking estimates that are at least as high as the station observations, and this is by design. We also see that for the West Coast data set shown here, Apple's rank 2 maximum shown in the purple and the Shake Alert grid product shown in the yellow generate shaking estimates that correspond well with median observations. And here are the same set of comparisons for the Japan data set in the bottom row. Overall, we see very similar behavior for apples, but for Shake Alert, we see that Shake Alert tends to have systematic overestimation in Japan, even larger than Apple's rank 1 maximum. And this is likely due to the shallow crustal rupture assumptions used in Shake Alert's ground motion models. But overall, these results suggest that the best configuration for achieving Shake Alert's goal of corresponding to median shaking is Apple's rank 2 maximum, shown in the middle. But now let's look at some alert quality results. Here are the alert quality results. The different colors show the different early warning options we tested, where different columns consider different alert threshold values relative to a target intensity threshold. The top row shows the fraction of target threshold locations that are alerted. The middle row shows the amount of precautionary alerts or below target locations that are alerted relative to the number of target locations. And the bottom row shows the fraction of precautionary alerts that are likely to still feel some shaking. So focusing on our preferred Apple's Rank 2 maximum configuration in the purple and the Shake Alert Grid product in yellow, we see that Apple's Rank 2 maximum tends to produce similar and sometimes better alert quality compared to Shake Alert using the same target threshold and alert threshold combination, where Apple's produces a slightly higher amount of correct alerts in the top row and a higher fraction of precautionary alerts that are likely still felt in the bottom row. And here are the warning time results. Like in the last slide, the different columns focus on different alerting strategies, and the top row shows the percentage of locations that receive at least some warning relative to the S-wave arrival, while the bottom row shows the percentage that has at least 5 seconds of warning relative to the S-wave arrival. Focusing on Shake Alert in yellow, we see that Shake Alert provides longer warning times at low alert thresholds compared to Apple's, and this is because it produces larger alert regions at these levels. However, Apple's is able to provide better warning times for higher target intensity thresholds, though there are still many late alerts relative to the S-wave arrival. We see greater improvements in warning times with Apple's when we switch from showing warning times relative to the S-wave arrival in the top row to warning times relative to when modified Mercalli intensity 4.5 is exceeded in the bottom row. We see that for higher target thresholds, even though many alerts arrive after the S-wave, alerts can still arrive a few seconds before significant shaking is exceeded when using Apple's, while alerts from Shake Alert still tend to be late. And once again, this highlights where Apple's could really improve early warning performance more generally if we integrate it into Shake Alert, especially because Shake Alert has technical users that have high target thresholds and use high alert thresholds. And that brings us to the end of my talk. Before I show my summary slide, I just wanted to highlight the references. Most of the work I showed is in a paper published in Geophysical Journal International from earlier this year. And with that, thank you very much for your attention.